for the presentation. Well, can you see the screen also? I guess presentation.
Yes, perfect.
Yeah. Okay. So yeah, hi everyone. Thanks, Alejandro, for your introduction. So yeah, my name is Oier Arcelus. I work as a postdoc at the group of Alejandro Franco. And in this talk, I will give more explanation, more details about the work that we did in the group that regarding the machine learning-based prediction of the electrolyte infiltration process in electrodes. So here you can see a bit of the outline of the talk. So we will briefly remind what the Lattice Boltzmann model is, even though what Eli already explained quite well. And from where did we get this inspiration to use machine learning for doing this kind of simulations? Then we will continue with the workflow that we used in this work, from the pre-processing of the segmented tomography data that we get to the multi-layers perceptron model that we used for the machine learning. So it's basically a neural network, going through the in-between data processing steps that we took. And we will show the results, including the training procedure, the predicted saturation values that we get, the 3D reconstructions of the electrolyte path, etc. So just to quickly remind what is the use of the Lattice Boltzmann method. So as you may remember from the Monday talk from Aosho DF, the Lattice Boltzmann method is basically coupled with the whole artistic manufacturing, electro manufacturing workflow in order to simulate the electrode infiltration process in 3D models, in 3D microstructural models, right? So as you can see from these videos, from a CGMD simulated electron microstructure, we can quite accurately see how the electrolyte penetrates, and particularly we can use this to assess the effect of unwetted zones within the electrode, as Eli explained, on the electrochemical performance of these simulated electrodes, right? And again, as explained on Monday also, different from molecular dynamics simulations, where in this case particle dynamics are resolved in a continuum. The Lattice Boltzmann method, what it does is it resolves the movement of the particles at the microscopic level in a set discrete lattice. So it has a set number of possible movements that it can do, and it's solved in this discrete lattice, right? And the interesting part of the Lattice Boltzmann method is that it's multi-physics, so it combines many different physics, such as the Navier-Stokes equation for the mesoscopic fluid flow due to applied external forces, but it also considers gas, fluid, and solid interactions in terms of the contact angles with respect to the solid phases. And also, it resolves Rayleigh-Taylor equations to account for fluid-fluid interactions in the interfaces between fluids of different densities. So here you have a small example. This is an electrode that is obtained from CGMD. And if you go and zoom a little bit more in detail, you can see one of these cells that the Lattice Boltzmann uses. And here you can see all the possible movements or preset movements that the particle can do to measure these dynamics, right? So the problem, however, as we already mentioned several times during the webinar, is that these simulations are pretty expensive. So in fact, relatively small amount volumes take several days of calculation to complete. And we wonder if it was possible to predict or at least capture the main aspects of the electrolyte infiltration dynamics in a porous electrode using machine learning. So particularly, we got the inspiration from this fun science divulgation YouTube channel. It's called the 2-Minute Papers. It's really interesting. And in this particular video, they showed some cool results from a collaboration between DeepMind in London and the University of Stanford, where they showed how they were able basically to predict fluid particle dynamics, and well, not only fluid particle dynamics, also granular dynamics. Let's say this is a simulation for sand, using graph networks, using as inputs physical models, right? So we thought that these results were really, really cool, and we were really inspired to try to do something similar, at least with our Lattice Boltzmann method. So yeah, in order to run the Lattice Boltzmann method, first, what we need is a voxel representation of the electron microstructure. So in this case, instead of using the CGMD structures, we used microstructures that were obtained with X-ray tomography, for which we have to thank our experimental collaborators in Germany. And as you can see, in this case, the volume was segmented to account for and the boxes of this microstructure were accounting for the active material phases, which were labeled in these black regions, and the pore phases, which are labeled in the white regions here. And then in order to perform machine learning for LBM simulations, we need to build a proper data set for the training. And for this, what we did was to extract 12 representative volumes from this big microstructure by taking their porosity as a control parameter. So this means that the sub-volumes were extracted with a minimal tolerance for their respective porosities when compared to the total porosity of the full microstructure, right? And after, what we did was to perform LBM simulations where each of these sub-volumes were simulated, or the electrolyte infiltration dynamics on each of these sub-volumes were simulated using 5 different applied pressures, and then leaving at least the rest of the parameters untouched. So in this case, from these simulations, basically what we obtain is a time series of voxelated data where each of the voxels contain the time evolution of the fluid density with respect to, basically with respect to time. So each of these voxels will contain a time evolution of the density. And the first thing that we found when we tried to build this data set for applying to machine learning was that we generated very, very large amounts of data. So if you took into account the 3D voxelated time series for each of the representative sub-volumes and the pressures, we generated around half a terabyte of data. And of course, this was the first wall that we found in the work, because we found that we were lacking the resources to perform direct machine learning prediction on the full fluid density time series. So basically for us, it would be too difficult to train a machine learning model that is able to capture the evolution of the density of each of the voxels in the microstructure, right? So then what can we do to find a smarter way around this? Basically, the first thing that we did is to realize that these voxels, and in concretely the pore voxels, where the fluid flow occurs, are not independent. So this means that, actually there is a whole body of literature that exists around finding these reduced representations of the pore spaces, which are also called pore network models, and which can be built in many ways. So for instance, we can, one way of building these pore network models is to fit spheres into the pore space, and then connecting these spheres with throats until you reach a given proper porosity for the microstructure. But they can also be built by further labeling or grouping pore voxels together given sort presupposed rules, right? So as you can see in this image, there is a very known but very beautiful algorithm that is called the Watershed Algorithm, which basically presupposes the rule of basin flooding. So it means that it takes different points of the pore space and it kind of mimics or simulates that this pore space is being filled with water. And then when there is a line of water that is touching, so if there is 2 different sources of water whose water level touch each other, then the algorithm, what it will do is create what is called a watershed line. And what it will do is to segment this pore space into independent objects, such as these ones, right? And of course, in our case, since we are segmenting the pore space, what we can do is to consider, let's say, these individual objects as individual pores of the pore space, even if, well, the definition of an individual pore is a little bit abstract, because the pore space, actually, it's a continuum. But we can segment our pore space and consider each individual pores like this. And particularly these methods, or these kind of methods that rely on labeling individual voxels, are very interesting because actually the data format of the output of the LBM simulations is exactly the same as the labeled pores. So we also have voxels that span the same spatial regions within microstructure. But in this case, instead of being labeled as different pores, it will be labeled just as liquid or void phases, right? And thus, these spatial regions can be perfectly correspond. We can do the perfect one-to-one correspondence between the watershed labeled pores and the LBM data. And in this way, we can exactly resolve which is the degree of wetting of each of the labeled pores along the full time series. So as you can see here, we can see how each of the pores independently fills with respect to the electrolyte inlet. So for now, if anything, what we have just done is increase the complexity of the data to analyze, right? So we went from having pores and active material to have different labeled pores. Then each of these pores have different degrees of wetting at different times. But actually, what is the information that we can extract from these concrete realizations? So first, we can show here a slice of a sub-volume where each of the individual pore is identified with a different color, as you can see here. And if we do a little zoom, what you can see is that each of these pores may be analyzed in terms of their structural properties, right? So let's say if we focus on this pore has a given volume. If we count the amount of voxels that it has, which is the gray area, it also has a surface area, which is this blue outline here. Additionally, the connectivity of the pores in question also can be assessed by in terms of the surface area that they share with the rest of the pore network, which is, as you can see in these red lines. And lastly, of course, the pores will be located at different distances with respect to the electrolyte inlet. And of course, this also will have an effect on the electrolyte infiltration process, right? So then, given this one-to-one correspondence, so given that the pores and the LBM module span the same spatial locations in the microstructure, what we can do is extract the individual saturation curves for each of these pores. So basically what we do is calculate the ratio of the volume that is occupied by liquid with respect to the total volume of each of the pores. And we obtain this kind of curves, which is basically this ratio with respect to the time, right? And we have this kind of curves for each of the applied pressures in this case. So if we continue with this data extraction, here we show another slice of the microstructure, as you can see here, yeah. And for illustration, we will select these two random pores, which are outlined in red and in blue. And also, as you can see, the saturation curves for each of these pores are shown also in red and blue. So what we did is to further distill this data in order to obtain the most relevant features of each of these calculated saturation curves. So basically, if you think about the saturation curves, they all have an onset, which basically represents that the fluid has started entering in the pore, which in this case happens at TF01. I mean, we call it TF01, you can call it however. And they also have a convergence point where no additional liquid is going to enter in the pore, right? And in this case, it happens at TF1, we call it. And then, of course, we have all the intermediate values of the saturation between the onset and the convergence point that basically define which will be the shape of this sloping region for the saturation curve. So all the rest of the data about the saturation, if you think about it, is just redundant, because once the pore is filled, doesn't matter how much time it passes, it will keep being filled. So all this thing is redundant, all this region. And the same happens for the starting region. So until no liquid is entering in the pore, of course, the pore will be empty. So saturation will be zero. So after doing this analysis, in the end, what you find is that from the half a terabyte of data that we generated, we ended up distilling this data to the most relevant features of the electrolyte infiltration process in 3D in a porous electrode. And we come up with a very simple data set that basically contains geometrical properties of the pores, such as you can see here, so pore volume 1, pore surface 1, etc. And the simulation conditions for the Lattice Boltzmann method. So in this case, we just changed the pressure. So this is what is contained in the dataset, but you can do for any other simulation conditions. And those datasets were used as inputs for a multi-layer perceptron. which is basically a neural network. And on the other side, we have the relevant features of the saturation curves, which were used as outputs for the network. So basically, the network was trained with some of these outputs, and it was trained to learn which is the correlation between the geometrical features of the microstructure and its saturation behavior. So yeah, this is the objective of this neural network, is that given a pore network model that is structured by Watershed algorithm or any other algorithm, which is the saturation curve of each of the pores that are contained within this pore network model. So before jumping into the training of the machine learning model, what we did was to give a quick look at the data, and we realized that first, the distribution data points for TF0 and TF1, so the starting and end times for saturation, were really sharp. So it meant that we could, in the future, encounter a problem of overfitting, in this case. So then what we did is to decide to apply a Box-Cox transformation. And this Box-Cox transformation basically means applying a logarithmic transformation to the data, which allows us to obtain a more homogeneous dataset, as you can see here, that then will allow to improve the performance of the model. So after training the machine learning model, in this case, we split the dataset into 80% training and 20% testing. We obtained the results for the prediction of the relevant saturation features. So in this case, for the saturation onset time, which is a TF0, and the saturation filling time, also the saturation end time, let's say, what we call TF1, we obtain a really very good predictions with relatively high R-square scores, around 95% in both cases, which of course partly is thanks to the transformation that we saw in the former slide. But then for the saturation values in between TF0 and TF1, the situation got a little bit more complicated. So in the beginning, we tried to predict the saturation values of 10 equidistant time steps between TF0 and TF1, which it means that we discretize the time steps between the initial and final saturation times, and we try to predict the saturation values that corresponded to each of these discretized time steps. So we were originally trying to predict this S set here. However, we found that if we wanted to predict all these points, the average R-square value that we obtained were not as good. So you can see here in the left side of this graph, the average R-square value, if we are trying to predict the full saturation value set. And we see that the average R-square value was around 83%. So it's still good, but it's not as good as we want, especially when comparing to the other two predictions. So what we did was to basically remove those saturation values that were not giving a good R-square value. And by subsequently reducing these data sets from the training data set, what we ended up seeing is that we were able to reach an average R2 square score of around 90%, which of course this was by deleting from the full saturation the S3, S4, S5, S6, and S7 values. And of course, this came at the cost of having less intermediate points to describe the shape of the saturation curve. So this basically leads to an incremental loss of accuracy for the reconstruction of the saturation curves, starting from the predicted saturation values, right? So it basically means that if we consider the saturation curve to be a continuous function, then if we are discretizing the points and trying to predict discretized points in this continuous function, the less points that we have, the worse the interpolation will be for this function, right? So we are basically incrementing the error for reconstructing the original saturation curves. But anyways, we tried to find a balance between these two competing effects, and we decided to go with this R-square value of 90% with an acceptable error, then if we were to take out more saturation values from the original set, this error will become too high and the R-square value will not improve too much. So we found that this was a good, let's say, balance. And then, yeah, basically, we trained the machine learning model like this. And then what we did was to apply the trained machine learning model to a completely new elementary subvolume, which was not part of neither the training nor the testing datasets. And we basically tried to reconstruct the overall saturation curves for the whole electrode, starting from these relevant saturation features of each of the pores. So basically, the way we construct the total saturation curves was by doing weighted sum of the individual saturation curves of each of the pores, and then let's say weighted by the ratio of the volume of this pore with respect to the total microstructure volume, right? Not to respect to the total pore volume of the original microstructure. So yeah, as you can see here, the results that we obtained were pretty good. So we are quite happy with these results here. And it shows that the model was really able to predict and reconstruct the total saturation curves when compared to the real and the predicted cases pretty accurately. So concretely, even if the saturation values, as you can see here, in the sloping region are a bit underestimated, the final saturation values and the saturation times, so it means that the convergence points and the time at which this saturation degree is constant, it's quite well predicted. And more impressively also, the model is perfectly able to predict changes in the applied pressure conditions, right? So here, as you can see, the velocity of the fluid and the saturation degree of the microstructure increases when we are increasing the pressure, the applied pressure. So this was a very nice result also. And well, of course, we think that this is promising. And but in this model, we just tried to increment or to apply different pressure conditions, but we didn't try to change any other parameters. And now we have a very diligent master student, Amin Malki, in the group that is really trying to push these boundaries and let's say trying to generalize the model in order to account for all possible properties of the fluid, right? So in LBM, you can vary the density of the fluids, the density of both fluids in this case of air and liquid, the contact angle, the viscosity, and of course the pressure. And so yeah, now we are trying to find a more generalized model for these saturation curves. And also an additional nice feature for this model is that since all saturation, so the features or the most important features of the saturation curves that we are predicting, in reality they are predicted on an individual pore basis, meaning that each of these pores will occupy different spaces and different regions in 3D inside the microstructure. We could as well reconstruct the 3D path that the electrolyte takes within the microstructure, similar to the videos that we shown earlier from the work of Abos or the videos that Eli showed last time in the former presentation. So as you can see here, this will be the electron microstructure at the first step in this case. So as you can see, there is already some liquid here in the real case, and the predicted case is still empty. However, when looking at the full time series, as you can see here, we can see that both simulations are really similar. I mean, they are totally consistent one with each other. There are some small differences. For instance, you can see in this region here, there is a pore which should be more filled because the real case it's a little bit more opaque, or the vice versa happens in this case. This pore should be a little bit more empty, right? But all in all, we find that these results are quite consistent. And actually, because in the beginning we were afraid that even if the saturation curves that we obtained were well predicted, we were afraid that there will be just some random pore in the middle of nowhere, right? That will start lighting up and becoming red. But this didn't happen, and actually the wave front for the liquid was quite well catched and predicted. So we are happy with these results. So yeah, here you can see the video. And lastly, what we did also was to perform an additional sensitivity analysis in order to better understand which was the effect of varying input parameters on the variability of the outputs. So basically, we defined the outputs in different groups. So of course, we defined the initial and final times for the saturations. And also we defined the initial saturation values. So the saturation values at the onset of the saturation curve and the saturation values at the convergence point of the saturation curve. And we are basically analyzing how varying pressure, pore surface area, pore contact surface area, so all the geometrical properties of each of the pores affects the indexes, the Sobol indexes, and affects basically the variability of the outputs of the model. So, well, in general, it's not obvious to obtain any clear physical insight in this kind of analysis. However, there are a few interesting things.
Oier, you have 5 minutes left.
Yeah. Okay, thanks. So first, we can see that the pore volume has a high impact on the initial and final times for saturations, followed by the pore surface area. This actually is in agreement with the conclusions from the Monday talk of Abos. And it kind of makes sense because the larger the pore is and the larger the surface area is, of course, the more likely it is to be well connected inside the pore network, right? So the fluid flow turns out to be easier in those bigger pores, which means that there is a bigger likelihood that the fluid will actually enter into the pores faster than in other smaller pores. Well, sooner, not faster, but sooner. And also we see that the pore location with respect to the fluid inlet has a high influence of SF0 followed by pore volume again. So it has a high influence on the saturation values at the beginning of the saturation curve. And actually also this makes sense because one thing that is visible, at least from our experience from LBM simulations, is that fluid velocity kind of slows down the more deep you go into the microstructure. So fluid velocity is not the same at the nearby zones of the electrolyte inlet with respect to going deeper into the microstructure, right? So of course, pore location affects the initial values of the saturation onset because depending on the fluid velocity, these saturation values will be steeper. So let's say that the saturation values will be steeper or not. So the saturation rate will grow faster or slower depending on the pore location in concretely. And lastly, we saw that all input parameters have more or less the same impact on SF0. So again, it's interesting, but we don't find any real physical meaning behind this. So in general, I will end with the conclusions. The main take-home message from this talk is the following. So we present a machine learning model. Basically, it consists of a multi-layer perceptron model, which is basically a neural network that is able to predict electrolyte infiltration in porous NMC electrodes, but we can generalize it for different microstructures. This MLP model is trained with data coming from LBM simulations and from pore networks extracted with the Watershed algorithm, but we could use any other method. So Watershed algorithm is not the only pore segmentation method that exists. We can have any pseudo-Coulomb methods or different kind of methods, but as long as the results or as long as the boxes are labeled in the same way or keeping the same data format as the outputs of the LBM simulation. And we found that our model correctly predicts the rate of saturation, the saturation degree, and filling time of the electrode quite fast and accurately, and the sensitivity analysis is performed between inputs and outputs. So the main appeal of this model or this tool is the computational efficiency. So first, as we saw, the generated data in LBM is around half a terabytes for all the training data that we generated. In turn, the MLP model just generates around, it's very simple Excel file with all the geometrical properties of the pores and all the most relevant features of the saturation curves. And it's just small tens of megabytes of data. It's nothing more. And same with simulation time. So in LBM, we take around 2 to 5 days to simulate. And on the contrary, in the MLP model plus, of course, obtaining the correct Pore network model, we obtain around, in our case, it was around 1 minute. But of course, this time will scale with the size of the system you want to predict, right? And also it depends on the watershed method. So basically, from all this 1 minute, 90% of the time it's taken into obtaining a correct Pore network model. And with this, I will finish. First, I will thank all the artistic team because it's really amazing that all these people, smart people, are together, right, doing work on batteries. And 2 collaborators, of course, to Jan-Lin Lee, Markus Ossenberg, Andre Hilger, and Ingo Manke, Jan-Lin Lee from Oak Ridge, and the Germans providing the data for the tomography. So thank you all. And with this, I conclude my presentation.
Thank you very much, Oier, for a very, very wonderful presentation. So this model paves the way towards a computational screening of electrolyte electroarchitecture pairs towards the optimization of electrolyte infiltration in along the manufacturing process, right? Because it's a tool that can be run fast, right? So thank you very much, Oier. This is, of course, a teamwork between Oier, Mark, and other guys from the artistic crew, and also for sure the colleagues in the States and in Germany. So, Fernando,
yes,
you have questions? Yeah.
We have a question. Let's see. So first, Oier, here you got a question from Rubayat Mahboub, who asks, is the tool / data currently publicly shared?
Not yet, but it will be in the future, of course.
Yes.
So for now, the model is very experimental. So still, we didn't test with very different microstructure types. So it's just one single NMC electrode, but we have to check against, let's say, ellipsoidal particle data or more fiber-like data. So still, there is it's very, very in its infancy, right? But yeah,
perfect.
At some point it will be.
I may add, Oier, as the PI of Artistic, is that definitely the model that Oier was explaining today will be publicly available upon the publication, right? As soon as the publication comes out, you can check already the preprint. I mean, it's already available. So Oier put in his presentation the link. But as soon as the paper come out, we will put in the Artistic GitHub platform. So we have access to the code for sure.
Here we have another question from Ming Che Han, who asks, when you compare the simulation results with real cases, how was the filling process in real cases measured?
Okay, when we talk about real cases, we are not talking about real experimental cases. It's physical simulations, right? So the real case, it comes from the LBM model, if that's your question. So it's not really an experimental measurement. It's more like the saturation curve coming from a physical model when compared to the prediction model.
Thank you.
Yeah, and I was explaining on Monday that it's very difficult to measure, the infiltration electrodes. So this is why, we rely to the Lattice Boltzmann model. Right?
Another question here from Celian Su, who asks, could you please comment on the prediction speed? Is it possible now with the machine learning to scale up the 3D simulation in your slide 11 for a potential comparison with, for instance, experimental data?
Yeah, this is one of the issues that have to be addressed in the future, because for now the training data set was built in microstructures that have dimensions of 100 by 100 by 75 micrometers. So then in the data set, we have one of the inputs of the data set is the pore location with respect to the electrolyte inlet. So the maximum value for the pore location can just be the maximum height of the simulation microstructure. So if you want to go beyond that, then we didn't test how the model extrapolates to bigger thicknesses, let's say. So of course, this is something that we must test, and but for now, I will be skeptical, but in the future, why not? Yes.
Perfect. Thank you for your answer. So here we have another question from Stefan Killian, who asks, He says, I might have missed it, but is it possible to account for different chemistries of the active material and of also the electrolyte?
Well, yeah. It is. This is more part of the LBM simulation. So the LBM simulation takes different inputs. So it takes the pressure for or at least the model that I was described in Monday. It takes the pressure for the electrolyte inlet, but it also takes the densities, the viscosities, and the contact angles. So the chemistry for the active material can be taken into account with respect to the contact angle, because of course, different chemistries will interact differently with different electrolytes, and these contact angles can be taken into account. But for now, for the model was just NMC 111 and the standard material for the artistic project. But of course, if you were to do the training using the same method, using different parameters, and actually this is what Amina is trying to do, of course, yeah, it should be possible.
Excellent, thank you. So we have covered all the questions, so maybe a quick typical machine learning question of my own before moving to the next speaker. So Oier, basically you took LVM simulations and you store all that knowledge, let's say, in your black box, which is your machine learning method, right?
Mm.
So are you sure? I mean, I imagine that there is always room to improve, but that all the experiments, or mainly simulations in this case, that you use to train this machine are, let's say, broad enough to describe the whole parameter space you're interested in improving?
I mean, in this case, this model was built, so of course, what you cannot do is perform the LBM simulation in the full data set for the whole tomography data. So what we did was extract different sub-volumes of this microstructure. So of course, the data set is kind of limited to the only microstructure that we have, from which we extracted the sub-volumes, right? So of course, we could have, the next step is generalize this. So the next step is try to train this model with the microstructure for NMC, but also fiber-like microstructures, ellipsoid-like microstructures, and then we will see really if our machine learning model, it really is able to capture all this variability in the microstructures. But of course, this is just a test.
Thank you.
Okay, so Fernando, I think we can move to the next speaker. Thank you very much, Oier, once again for a very nice presentation, all the work you are doing in the team. It's a real pleasure to work with you, Oier.
Yep.
Thank you.
Thanks.